So when you take an aromatic hydrocarbon, especially you take a very simple benzene, and if you treat it with dichlorine in presence of FeCl3, you will find a chlorobenzene is formed. Now to this, if I am going to add second time another chlorine, as I said before, chloro group is an ortho-para director. What is the nature of the chloro group? It is an ortho and para director.
So para will be the major product, right, sir?
Perfect. So you'll get the dichlorobenzene, in which the para will be the major, while the minor will be in the ortho. So the newly added chlorine can come either in the ortho portion or in the para. As you said, major will be the para dichlorobenzene.
Oh, yes, sir.
Now, depending on the group that is attached to the benzene ring, the incoming group can go to any position. For example, instead of chlorobenzene, if you are going to take a molecule like nitrobenzene, and if you are going to do chlorination to that, so you'll get only one possible product, that is.
Sir, why are we adding FeCl3, sir, with Cl2?
Very good. Unless until you add FeCl3, the electrophile will not be generated.
Okay, sir.
So, meta-nitro chlorobenzene. So depending on the group that is attached to the benzene, what product you get will be decided. Okay?
Yes, sir.
When you look into the reaction, preparation of aromatic hydrocarbon, aniline plays a very important role, but not the direct form of aniline will react. So aniline is nothing but aminobenzene, or the IUPAC name of aniline itself, aniline as well. But the correct IUPAC name for aniline is aminobenzene. So just treat it with 0 degree to 5 degree centigrade. Treat it with NONO2 in presence of HCl. So you'll get the NH2 will be converted to N2Cl. So that is aniline, and this is called as benzene. Very good. Benzene diazonium chloride.
Yes, sir.
What is the speciality of benzene diazonium chloride? This is a raw material. Using this, you can prepare any halo compounds. For example, if you treat benzene diazonium chloride in presence of Cu2X2, so X can be Cl or Br. So you can get the corresponding chlorobenzene or bromobenzene, whatever you are using.
Yes.
Similarly, you can also treat this with copper in presence of HX, where X will be equal to Cl or Br. Again you have the benzene ring attached to the halogen. So this reaction is called as Sandmeyer's reaction.
Okay.
This is called as Gattermann's reaction. No sir, I want to prepare only iodobenzene. It's very simple. Just add aqueous KI and shake the test tube well. To the benzene diazonium chloride, add aqueous KI and shake it well. So if you do that, automatically iodine will get added up to that. Simultaneously, you can even do one more reaction. So this is halobenzenes, either chloro or bromo. The last one is a very peculiar reaction. We call this as Bals-Schiemann reaction. This Bals-Schiemann reaction is used to prepare fluorobenzene. So for this, what am I supposed to do? I need to add HbF4. So the hydrogen and the chlorine of the benzene diazonium chloride will be removed. So I will get an intermediate like this. Okay, so this is an intermediate. So I can put minus HClB into it. So this intermediate, again, when you heat it, it undergoes rearrangement or reorganization. Like the fluorine will go and attack the benzene and the nitrogen will come out. So what all removed? Nitrogen is removed, BF3 is removed. So what is left over? Benzene ring.
And one fluorine.
One fluorine is attached. So you get a fluorobenzene. Make a note mark. So using benzene diazonium chloride, you can prepare all the 4 halogens. Exchange reaction. So when you do an exchange reaction, you can prepare both fluoro and iodocomplex. So let me explain. So there is a reaction called Schwarz reaction.
Yes, sir.
So in this reaction, you will get the fluoro gets exchanged. For example, you take any RX, and remember the X should be fluoro or bromo.
Yes.
So you have to treat this with AgF. So now what will happen? AgX will be removed, minus AgX. So your final product would be RF. So fluorobenzene, Schwarz reaction. So what is the application of Schwarz reaction? This reaction is useful in preparing chlorofluorocarbons, CFCs.
Yes, sir.
So what is chlorofluorocarbon? For example, you take carbon tetrachloride and treat it with 2 moles of AgF. Minus 2 moles of AgCl will be removed, so you'll get CF2Cl2. This is called as dichloro-difluorocarbon, which is actually a coolant.
Yes, sir.
Similarly, if you take another reaction that is called as Finkelstein's reaction, or it is called as Cronin-Finkelstein's reaction. Both are same.
Yes, sir.
So here you take RX again and treat with sodium iodide. For this reaction to happen, you have to do the entire reaction in the acetone medium and make sure the acetone is dry. I'll explain why it should be dry.
Yes, sir.
So when you take the R, the NaX will be removed and you have Ra. So what is the necessity to add dry acetone? First point, if the acetone is not dry, the reaction will not take place because the NaX will dissolve. So you have to make sure the acetone is dry. Okay. So if the
Yes, sir.
acetone is dry, how to make the acetone dry?
Heat it, sir.
If you heat, acetone will be evaporated. Make a note.
Yes, sir.
If you add calcium, anhydrous calcium chloride to acetone, it will absorb the water molecule and keep it as a water of crystallization. Thereby you can make the acetone dry. Now what will happen? As soon as the NaX is formed, it will get precipitated. I mean, it will not be dissolved. So when it gets precipitated, what will happen? The equilibrium will shift towards right hand side. So thereby more and more alkyl iodides are prepared. So the NaX will be precipitated. Thereby what will happen? Equilibrium shifts towards product side.
Yes, sir.
So when the equilibrium shifts towards product side, automatically more alkyl iodides are prepared. Copy mo.
Yes, sir.
Here again you need to understand one more point here. That is, in Schwarz reaction, not only AgF is used, you can also use SbF5, or you can also use arsenic fluorides. But arsenic fluorides are generally not allowed because it's very it's very, very dangerous. So normally we don't use it. It's poisonous too. So we just use only stibine, that is antimonial fluorides, and silver fluorides. Okay. So that is about the exchange reaction. Now let us go for the next reaction, that is, though the reaction is not much highlighted in the textbook, questions are being asked. So for the sake of that, we have to learn this reaction. This is called as allylic bromination, or we call it as allylic halogenation reaction. So what do you mean by allylic halogenation? So you take any molecule which has an sp3 carbon attached to an sp2 carbon. For example, this is propene, this is cyclohexene, this is butene, 2-butene, this is but-1. So all of them are having allylic carbon. So which is the allylic carbon? Here there is one allylic carbon, here there are two allylic carbon, here there are two allylic carbon, here there is only one allylic carbon. That is, so what do you mean by an allylic carbon? Please make a note. An allylic carbon is nothing but an sp3 carbon attached to an sp2 carbon. So this sp3 carbon is called as the allylic carbon.
Yes, sir.
So the reagents that can be used for this reaction would be, either you can use bromine or you can use chlorine heated at 773 Kelvin. That is one reagent. Adilana, you can use bromine or dichlorine in presence of light, UV light. Or you can use a reagent called NBS. What is the full form of NBS? N-bromo succinamide.
Okay, sir.
So now you just treat it with any of the reagent. I will be in for CBSE. The first two will do. You need not go for the third one. It's an extra point I'm giving you. So
okay, sir.
You use just bromine in presence of light. So what will happen? At the allylic position, bromine will get attached.
Br will be attached.
Similarly, here
here it will get attached. It can attach
anywhere. So again, we have another limitation here. So Br2 bar 773 Kelvin. So you can either attach in any of the corner.
Yes, sir.
You can use anything, okay?
Yes, sir.
I will show you how this N-bromosuccinimide is formed. First you copy this, then I will let you know.
Okay.
Preparing N-bromosuccinimide. So this is your succinic acid. Okay? Succinic acid is nothing but butane 1,4 diazic acid. So now what are we supposed to do? We are going to treat it with 2 moles of ammonia and heat it. So when you do this, what will happen? You will find an imide form. That is, this is called as succinimide. Succinimide. I have written amide, it's wrong. Succinimide. So to this, if you treat a bromine with this, minus HBr will be removed. Thereby you get something like this. N-bromosuccinimide. So this is a very good reagent for doing halidic halogenation. Okay, CBSE you don't have this, so no need to study. Just an extra info. So halidic halogenation, if you know, bromine and chlorine are being added in presence of light or higher temperature of 773 Kelvin, that will do.
Yes, sir.
Right. Now shall we move forward to the next method?
Yes, sir.
So with this, all the preparation of alkyl halides over.
Yes, sir.
Now we are getting into the next part, that is called as the physical properties. So when you talk about the physical properties, number one, whenever you find the mass of the mass of the halogen increases, such as iodine is more heavier than the bromine, bromine is heavier than the chlorine, chlorine is heavier than the fluorine.
Yes.
So whenever the mass increases, melting point and boiling point will automatically increase. Similarly,
Yes, sir.
when the number of carbon chain or the carbon number increases, melting point or boiling point will increase.
Sir, the second one is indirectly the first one, no, sir?
What is it? I didn't understand.
Like, if number of carbon increases, the mass of halogen increases. So both of them are same, right, sir?
Yeah, both of them are going to be same, but they are different points, right?
Yes, sir.
So melting point or boiling point will increase even if the carbon's mass is going to increase or the halogen mass is going to increase, it's going to be the same. Now, very important aspect. What will happen to the carbon chain? Remember, when the carbon chain is bigger or lengthier, melting point and boiling point will increase. Anyway, if the carbon chain is shorter or lengthier item, it is shorter,
Yes, sir.
then it will be the reverse. That is, the melting point and boiling point will decrease.
Okay.
For example, you take this is N-butyl chloride. This is secondary butyl chloride. This is isobutyl chloride. This is tertiary butyl chloride. If you check, all of them will have same mass. Not only mass, their molecular formula is also same, right?
Yes, sir.
C4H9Cl, correct? H11,
Correct.
I'm sorry. C4H9Cl. So all of them will have the same molecular formula, but you know, the longest carbon chain, this will have a
Most.
higher boiling point, while this will have lower
Yes.
boiling point. Why the same molar mass, but why there is a difference? Please make a note. You know the reason?
Because it has more branching means less boiling.
Correct. அது எப்படி கரெக்டாக சொல்லணும்? Right up.
Yes, sir.
Lesser the surface area,
Yes, sir.
less will be the boiling point or melting. So the boiling point or melting point depends on the surface area of the carbon also.
Yes.
Sir, what are the other factors? As the number of halogens increases, melting point and boiling point will also increase.
Yes.
Greater the number of halogens, greater will be the melting point and boiling point. All those aspects. Now we are going for the solubility. Solubility in water. We all know that organic halogen compounds are polar.
Polar, right?
So organic halogen compounds are polar because of the difference in their electronegativities. Carbon is less electronegative, halogens are more electronegative. So being more electronegative, what will happen? There will be a charge difference. So if you look
Yes,
into
sir.
the electron density diagram, upon the halogen more electron will be there, carbon will have less electron. So what
Yes,
you
sir.
understand from this, there is a difference in the charge, there is a polarity. Because of this, dipole moment has also been noted. Now the point is, in spite of being polar, please make a note, in spite of being polar, haloalkanes are insoluble in water.
Yes, sir.
Haloalkanes are insoluble in water in spite of being polar. What is the reason? Why do you think it's in spite of being there is a charge difference, polarity is existing, yet it is not insoluble in, it's insoluble in water. Why it is not showing solubility in water?
So because the hydrogen bonding is
Excellent.
able to. Great.
So absence of hydrogen bonding. There is no hydrogen bonding at all.
Uh,
Unlike all the other molecules like alcohols, aldehydes, there will be a little bit of hydrogen bonding which is not noticed in haloalkanes.
yes.
So the haloalkanes do not have hydrogen bonding, or even they form, it will be of very less intensity. Maybe I think chlorine will form with water, but you know the gradient of formation of that hydrogen bonding is not much prevalent with other electronegative atoms like nitrogen, oxygen, and fluorine.
Mm.
So hence you
Yes.
cannot say that it will be soluble in water.
Okay. Sir.
What about chlorobenzene? Chlorobenzene will not form at all. At least halobenzene, haloalkanes can form. Haloarenes cannot even, you can't even think about them forming getting dissolved in water, because benzene ring is a very important factor in solubility, because it is
Yes, sir.
highly hydrophobic in nature.
Okay, sir.
What do you mean by hydrophobic?
It. I
Hydro
mean,
means
it will
water,
water.
phobic means fearing. So because of its bigger benzene ring, the benzene ring is so big that it will not be soluble in water.
Yes, sir. Yes, sir.
Done?
Yes, sir.
So I even talked about the dipole moment, right?
Yes, sir.
So this dipole moment plays a very important role in the molecule's polarity and its solubility in the polar or non-polar, whatever the solvents you take. So let us take the methyl chlorides.
Yes, sir.
So let me draw this. So in the first case, there are 3 hydrogen and 1 halogen. So the halogen be the chlorine. In the second case, there will be 2 chlorine and 2 hydrogens. In the third case, only 1 hydrogen. In the fourth case, there is no hydrogen.
Yes, sir.
So first one is monochloromethane, dichloromethane, trichloromethane, tetrachloromethane. So when you write the dipole moment, what will happen in all the other cases? It will be moving towards the chlorine.
Yes, sir.
In the last case, all the dipole moments will be cancelled because the resultant pull is actually nullifying each other. So carbon tetrachloride will have 0 dipole moment, 0 divide. While the others will have some kind of dipole moment in them, because the electronegativity difference is of much difference. In this case, carbon is more electronegative, so the dipole moment moves towards the carbon. Again the same thing over here, the reverse. So here the dipole moment will be towards the carbon. So dipole moments plays a very important role in their solubility in any solvent, such as polar or non-polar.
Yes. Sir, so which will have the highest dipole moment, sir?
Obviously, I think methyl chloride, monochloromethane should have, no?
Okay, sir.
As the chlorine increases, I think it will get relieved. The concentration of the electron will get relieved towards the chlorine, no, in the opposite direction. So I think the dipole moments will automatically reduces.
Yes, sir. Yes, sir.
You want the exact value?
No, it's fine, sir.
Normally they don't ask for values and all. We can show. I'll get you the exact values if you want. In our future, if you want to refer, you'll get some idea.
Yes, sir.
Okay? Just a moment. So this is 1.89 dBi, D for dBi. Here mu
Yes,
is
sir.
equal to 1.60 dBi. And for trichloromethane, it is 1.04 dBi. So it's very evident, right? The
Yes, sir.
dipole moment is getting reduced.
Correct, sir. Yes, sir.
Done? Copy?
Yes, sir.
So we have seen the melting and boiling point, we have seen the solubility in water, we have seen the dipole moment. Now we have to look for the next aspect, that is halobenzenes, especially when you take the dihalobenzene. That is, when you take a dihalobenzene, there are three types of dihalobenzenes, right?
Yes, sir.
It can be the ortho isomer, or it can be the meta isomer, or it can be para isomer. So among the three, which one is more symmetrically aligned?
Para.
Perfect. So since para is perfectly, it's symmetrically aligned, you can place it in a particular crystal lattice or in a molecular lattice. Perfectly, you can arrange them without wasting the space. So because of this symmetrical arrangement in the lattice, it will have quite a higher boiling point and melting point. Okay, one of them will be quite high because of its symmetrical arrangement. So this symmetrical arrangement makes it to be a very, very strong arrangement. Thereby you have to apply very high amount of heat to melt it out. I think most probably boiling point will be more. Melting point will not be that much, but boiling point will be more. You can refer the textbook for that. So the reason is the symmetrical arrangement of this particular molecule in the lattice.
Yes, sir.
So that is all about the physical property, the solubility, dipole moment, and then melting and boiling point, and then the symmetrical arrangement of halobenzenes. So this is all about the physical property. Either we have something called density, various other things are there, but NCERT andalavuku they have not discussed, so let's not get into it. Okay?
Okay.
Right. Shall we move forward?
Yes, sir.
Yeah. Now let us go for the reactions of halo compounds or haloalkanes. So most of the reaction of haloalkanes are perfectly nucleophilic substitution reaction. So
Yes.
what is a nucleophilic substitution reaction? When you take an alkyl halide, a nucleophile is a positive charge loving species. So on itself will have a negative charge. So it will attack the alkyl halide. When it attacks the alkyl halide will lose the halogen and gets itself attached to the nucleophile, and the halogen is released. So this is called as the substrate, while this is called as the nucleophile. This is your perfect product. Don't say X minus is a byproduct. It is called as nucleofuge. When the same X minus is attached to the substrate, it gets a different name. Any idea what is it called? Leaving group. But in your textbook and all your guidebooks, they would have mentioned X minus as leaving group. Actually, X minus is already a left group. So in English, you cannot use the word left group. So you should not use a leaving group after it got left. So the better term is nucleofuge. But the same X, when attached to the substrate, which is going to be replaced by the nucleophile, it will be called as leaving group before the reaction. Make a note of this. This is a very, very important point. So this basics is going to continue.
Yes, sir.
What are the two types of nucleophilic reaction? So number 1, SN1 mechanism. Number 2, SN2 mechanism. Number 3, SNI mechanism. So in CBSE you don't have SNI mechanism. So we will see only SN1 and SN2. Okay.
Yes, sir.
So very simple, when you take an SN1 mechanism, there are certain steps to be followed. For SN2, we will have steps to be followed. So what will you do? You draw a tabular column. Pencil எடுத்துக்கோ, scale எடுத்து அழகா ஒரு tabular column போட்டுக்கோ, separate pagesல. இந்த page வேண்டாம், separate page you write. So draw SN1 and SN2 like this in a column and keep it ready. Once I mention, the points, you can write down the points there simultaneously.
Okay, sir.
Okay? So, முடிச்ச உடனே சொல்லுமா, we will move forward. So, let me repeat. So, there are two types of reactions such as SN1 and SN2. SNI is not there. So, SN1 reaction, it's a two-step reaction. The first step is a slow step, which is the rate determining step. Second point, rate will be dependent on the substrate alone, that is alkyl halide only. Third point,
Yes, sir.
tertiary alkyl halides or secondary with bulky beta crowding is always takes place SN1 reaction. What is the salient feature of this particular reaction? Formation of carbocation, which is nothing but your slow step or the rate determining step. Fifth one is the polar protic solvent, where you use solvents with proton, so their polarity is quite high. Very important point is the next point. Since this reaction is independent of the nucleophile, even a weak nucleophile works well for an SN1 mechanism. The last before point, carbocations are formed, so rearrangements are possible. The last point is optical activity, which will be separately taught to you. So as of now, for the sake of writing the point, please make a note. The optical activity in SN1 leads to racemization. Sir, what is the meaning of racemization? Later I will explain. Okay?
Yes.
So is the points clear? Are the points clear to you?
Yeah.
Good. Now shall we go for the mechanism? So what kind of carbocation should I use in this case? Tertiary tertiary halide should be used, I say. Correct?
Correct. Yes, sir.
So what is the step 1? It is formation of carbocation. So the first step, you add the potassium, so minus KCl, so you'll get
Sir, can you explain again how weak nucleophile also it works for SN1?
when I go to the factors affecting nucleophilic reaction, anga I will give in detail. What you need to understand in the reaction, there is no what you can say nucleophiles indulgence in the reaction rate. The rate will not be affected by nucleophile. Even a weak nucleophile can give you a product because the product depends only on the carbocation stability. I told you even a weak nucleophile works well. Okay, now look at this. This is a very very important factor. I want you to have a look into this. This carbon is sp3 carbon. What is the shape?
That's right.
Now it is becoming sp2 carbon. That means it becoming a planar molecule. So from a 3-dimensional shape, it is becoming a 2-dimensional planar. And tertiary carbocations are well known for their stability, isn't it?
Yes, sir.
Why tertiary carbocations are stable?
Sir, because they are planar.
அவ்வளோ ஈஸியாக சொல்லிடுவாங்களா என்ன? Because methyl is an electron releasing group, இல்லையா? Methyl is an electron releasing group. So electron releasing, it will leads to plus I group or plus I effect. So this plus I effect will supply electron to the central carbon.
Yes, sir.
So central carbon is already having a positive charge. So the positive charge, or you can say the starvation of the electron, is satisfied by the carbon giving the electron to the central carbon. So this is through plus I. Or have you heard about the term called hyperconjugation, no bond resonance, Baker-Nathan's effect?
Yes, sir.
And the carbon irukkakudiya hydrogen oda electron will come to the central carbon and satisfy it for some time, again it goes bond. So this also leads to the stability of carbocation. So carbocation stability can be explained either by inductive effect or hyperconjugation. But as an organic chemist, if you ask me, I will tell, compared to inductive effect, hyperconjugation is a better stabilization effect. Okay,
Yes, sir.
so bear that in your mind. Right, now let us go for the step number 2. So step 2 is with nothing but attack of nucleophile.
Yes.
What did I say? The first step is slow step in sonna nyabam iruka?
Sir.
And this will be your rate determining step. Similarly, the second step, that is attack of nucleophile, is a fast step. Okay?
Yes, sir.
So the attack of nucleophile will be very fast. So Br minus will come on attack. So I will get again from planar structure. நான் எங்கேயே போட்டிருக்கணும். It's okay. So already halogen is going out. So instead of halogen, I will put something else. OH minus. So what is happening from the
positive charge on the earth, it's adding HO.
அவ்வளவுதான்.
Okay, sir.
From planar structure, it is becoming tetrahedral. Copy ma. So what do you mean by SN2 mechanism? Again, here you have the points. What is the first point I gave for SN1?
It is a two-step reaction.
It is a concerted reaction. அப்படின்னா என்ன அர்த்தம்? A single step reaction.
Yes.
What is the second point I gave?
Rate K is equal to substrate. That's
Here the rate will be dependent on the substrate and the nucleophile that you use.
Oh, okay, sir.
Here the substrate is Rx, so make a note of that. What is the third point?
First step is low, rate determining step.
Okay, fine. Here அந்த மாதிரிலாம் எதுவுமே கிடையாது இல்லையா? So rate determining step அந்த மாதிரி we don't have any particular so third point one.
3-degree alkyl halide.
So tertiary alkyl halides and secondary with a bulky beta crowding I said. So இங்கே என்னன்னா primary alkyl halides will undergo mostly, or you can use secondary, but beta crowding should be less bulky. Okay. What is the fourth point?
Formation of carbocation.
So I said that is the salient feature of that particular reaction, correct?
Yes, sir.
இதோடைய salient feature என்னன்னா it will undergo a rear side attack. If there is a nucleophile, opposite of the nucleophile, if there is a nucleophilic attack, the leaving group will be there, right? Opposite of the leaving group, it will come and attack. That's what rear side attack, which leads to a very unstable, temporary, pentavalent transition state will be formed. Remember, carbocation is an intermediate which can be isolated from the solution. Instead of adding OH, if you had some strong nucleophiles, it will go and attack immediately and form a product. That means carbocation can be isolated. In the unstable temporary pentavalent transition state is very short-lived. It is a very short-lived. அதனால you cannot isolate it.
Yes, sir.
Okay. And what is the next point, ma?
Sir, the third point, what is after 2 degrees, sir?
2 degree can be used, but you have to use with beta crowding of less bulkiness.
Oh, okay, sir.
அங்கே more bulky beta crowding ஓட யூஸ் பண்ணலாம், இங்கே less bulky beta crowding ஓட யூஸ் பண்ணலாம்.
Okay, sir. Yes, sir.
Right, what is the next point, ma? After the fourth point, fifth point?
Polar protic solvent.
So இங்கே வந்துட்டு there is no polarity. There was a charge separation, right? Here there will be no charge separation. So you have to use polar aprotic solvent. But still it should be polar in nature. ஏன் polar aprotic அப்படின்னா it should not give too much of proton. At the same time it should be polar, because we all know that haloalkanes are polar in nature. Without polarity, if you add something else like benzene or toluene dissolve agadu, because it is already having a polarity. So polarity should be there, but it should not be too polar. Irukano ana irukakudadu, like that. So for that you can use molecules, substance like DMF, dimethyl formamide, DMSO, dimethyl sulfoxide. So these kind of reagents you can use. So what is the, not reagents, solvents. They are all polar aprotic in nature. Okay. Now tell me, what is the next point?
Even if the nucleophile is weak, it works.
Inge weak work out agadu. Only strong nucleophiles will react. Why? Because the rate itself depends on the nucleophile.
Oh, correct.
Because the rate itself depends on the nucleophile. Next step.
Yes. Since carbocation is formed, rearrangement happens.
Rearrangement is impossible.
Yes.
Rearrangements are impossible. Why I am saying it's impossible? Because when you try to do a rearrangement, what will happen automatically? It should have a carbocation which should undergo such a intermediate, such an isolable, English isolable intermediates are very very rare in case of SN2 mechanism because it forms a temporary, unstable, pentavalent, short-lived transition state. So rearrangements are impossible. What is the last point?
Optical activity.
Again, optical activity is beyond your scope now. So optical activity leads to total inversion. I'll talk about this total inversion and other things when I teach optical activity. Okay?
Yes, sir.
So have you made a note of all the points?
Yes, sir.
Shall I go for the reaction?
Yes, sir.
Super. So be careful with this particular reaction. So we have this is a primary alkyl halide, that is I'm going to take a methyl halide. Okay.
Okay, sir.
So methyl bromide எடுத்துக்கலாம். Bromide is a better leaving group, yeah.
Correct.
So I'm going to add as usual aqueous KOH. Who's the nucleophile here? OH minus. He will come and attack from the opposite side of the bromine.
Sir, so the SN2, sir.
It is SN2 mechanism, of course. So இப்போ என்ன ஆகுதுன்னு பாரு, இதான் ரொம்ப முக்கியமானது. Watch carefully. So the carbon is here. One part will be in the front, another part will be in the back, one part will be on the plane, while the bromine will go out by taking the electron, while OH will donate the electron.
Yes.
So this is a pentavalent transition state and it is very 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 short-lived. Okay. So the reaction மாதிரி ஒன்று ஃபார்ம் ஆகுதுன்னு சொல்கிறதுக்குள்ளேயே the product form ஆயிடும். So Br minus goes out. So you'll get methanol. So this is a pentavalent short-lived transition state.
Yes.
So now you are clear?
Yes, sir.
So that
Yes,
is
sir.
all about the substitution nucleophilic reactions. Right?
Yes, sir.
Now I want you to do an activity kind of thing. Based on the tabular column that I have given and based on the points, will you be able to build a mind map kind of thing? எப்படின்னா,
Yes.
so first வந்து substitution nucleophilic reaction. நான் ஷார்ட்கட்டில் எழுதுகிறேன், நீ எழுதிடாத. அந்த மாதிரி ஒரு பாக்ஸ் மாதிரி போட்டுட்டு அதில் ஃபஸ்ட்டு SN1, அதில் என்னென்ன பாயிண்ட்ஸ், அதில் அதே மாதிரி SN2, அதில் என்னென்ன பாயிண்ட்ஸ்,
Okay.
அந்த மாதிரி போடுங்க. ஒரு 5 மினிட்ஸில் பண்ணிடுவீங்களா?
Yes, sir.
வளவலன்னு எழுதக்கூடாது, எனக்கு வந்து பாயிண்ட்டாக எழுதணும். இப்போ SN1ன்னா என்ன வரும்? ஃபஸ்ட்டு டெர்ஷரி ஆர் பல்கி செகண்டரி, இங்கே வருவது பிரைமரி ஆர் லெஸ் பல்கி செகண்டரி, போலார் புரோட்டிக், போலார் ஏப்ரோட்டிக், டெசிமைசேஷன், இன்வர்ஷன் அந்த மாதிரி எழுதி ஒரு ஃபோட்டோ கிளிக் பண்ணி என்னுடைய கிளாஸ் ரூமில் அப்லோட் பண்ணாலும் சரி, சேட்டில் அப்லோட் பண்ணாலும் சரி, இட்ஸ் லெஃப்ட் டு யூ. ஸ்டார்ட்.